search through a sorted list of data, the standard approach is to use a binary search. The algorithm checks the exact middle of the list, asks if the target is higher or lower, and then discards half the data. It works, taking logarithmic time, but it ignores the actual numbers it is looking at. Imagine if an algorithm didn't just guess the middle every time. Imagine if it could look at the data values and calculate where the target actually sits. This map covers 50 essential computer science algorithms. In the searching category, we find algorithm number 8, Interpolation Search. True algorithmic speed comes from mathematically predicting exactly where data should be, rather than just eliminating where it isn't. This diagram illustrates a familiar human habit. If you need to find the name Williams in a physical phone book, you don't open to the exact middle and start having the pages. You know W is late in the alphabet, so you flip the directory open near the back. You are using the value of the name to estimate its physical position. W. W. Peterson formalized that instinct into an algorithm in 1957. He was addressing a specific hardware constraint, prioritizing the physical location of records over theoretical proofs. Early storage systems relied on magnetic drums and disks, where moving the mechanical read heads across the drive was slow. Peterson needed to calculate where a record lived based on its value to avoid wasteful mechanical scanning. For 2 decades, the speed gains of Peterson's method were passed around by programmers as folklore. In 1978, researchers Pearl, Itai, and Avni published the mathematical proof confirming how fast this heuristic really was. Human intuition for flipping through pages was translated into a mathematical function to bypass the severe hardware limits of the 1950s. The mechanical distinction is straightforward. Binary search asks, is the target higher or lower than the midpoint? Interpolation search asks, given this target's value, where exactly is it in the array? It works through a linear translation. If your target is 75% of the way up the total value range, the algorithm probes 75% of the way up the physical index of the array. This logic carries a requirement. The data must be sorted and uniformly distributed, meaning the numeric gaps between the records are relatively consistent. By assuming the data follows a predictable, even pattern, the algorithm skips the repetitive halving steps and makes accurate leaps. We are searching for the target value 64. Binary search averages the indices. It lands on index 5, value 48, missing the target. Interpolation calculates the target's distance over the total value range, multiplying by the index positions. It outputs index 7, finding 64 instantly. To execute this safely, the code uses a while loop guard condition. The loop only runs while the target number falls within the lowest and highest values currently bracketed, preventing out-of-bounds errors. By leveraging basic algebra, the search window collapses on the target almost instantly, instead of having it over and over. At massive scales, the math pays off. For an array of 1 billion items, a binary search requires about 30 probes. An interpolation search needs about 5. This efficiency makes it effective for specific tasks, like querying sequential database IDs, searching evenly spaced timestamps, or locating indexed physical records. But if your data is skewed or clusters exponentially, the mathematical estimation fails. When one huge outlier warps the math, the guess barely moves the search window. It degrades into a linear search, examining one item at a time, slower than a standard binary search. That is the ultimate trade-off. The algorithm abandons a guaranteed worst-case safeguard to relentlessly exploit perfect data distributions. The Python implementation of this search is concise. The strategy hinges on this single line of code that calculates the midpoint. If you replace this specific line with a simple average, the whole function reverts back into a binary search. You can find the full code for this algorithm, along with 49 others, in Imran Ahmed's book, 50 Algorithms Every Programmer Should Know. Next time, we move to the divide and conquer design strategy. Thanks for watching.